Welcome back. We are part 2 of section 7.2, talking about gases and gas laws. So last time we talked about Boyle's law and the relationship between volume and pressure. And now we're going to talk about Charles' law, the relationship between volume and temperature. If you recall, Boyle's law was from 1662. And here we are, 140 years later. Yes, it took 140 years for someone else to figure this out and write it down. But hey, we got it. Okay, so Charles' law was actually a French balloonist, as in hot air balloon, determined this, and that would make some sense when you think about what a hot air balloon is, right? Is that it fills with air, and then you heat that air up, and thus it rises above in the air, right? But anyway, the relationship itself is, again, one of those is almost so common it's almost intuitive. The volume and temperature of a gas are directly proportional. As one goes up, the other goes up, if the pressure is constant and the amount of gas is constant. That's always the key. So here's another example. Notice in the top the same mass, which indicates that pressure is constant. So there's equilibrium right between that 2 kilogram mass and the pressure of the volume of the gas. So this one would be like on a hot plate or under a fire, and the temperature doubles and the the volume doubles. But notice that the temperature is in Kelvin, right? That's important. And then we get a nice straight line relationship. Temperature going from 5 degrees Celsius to 10 degrees Celsius doubles in Celsius, but it's not really doubling, right? It's actually a very small change, so we need to use Kelvin. Okay, now, just like last time, we can look at if volume and temperature are proportional, then the ratio must be proportional to 1 or to a constant, depending on the units. And so, as we see here, right, under different conditions, that ratio is still equal to the same thing. If two things are equal to a third, then they're also equal to each other. And we can write Charles' law as V1 over T1 equals V2 over T2. That's the important equation. Right. One quick note before we do an example. I just think this is super cool about the Kelvin scale, which actually can be derived from Charles' law. If we plot volume and temperature, right, just like we did in the last slide, right here, we get a nice straight line. But of course, at 0 degrees Celsius, the volume is not 0, so it has some value here. And we also learned from Boyle's law, right, that as volume goes down at a given temperature, pressure increases. So we can actually draw different plots of volume temperature at different pressures. That's what we see here, these three lines. But they have different slopes. The cool thing is, if you actually experiment with this and take a bunch of measurements, we find that they all converge at a point right here, right? And they all converge at the x-axis. And think about if this were to continue on, we'd be talking something like negative volume, and that has no meaning. So this is really like as far as it can go. And they all converge at negative 273.15 degrees Celsius. And that is 0 Kelvin. It's absolute 0. So that's the temperature scale. It's a very simple conversion. It's just a shift from 0, but it does show up here using Boyle's law and Charles' law, which is quite cool. Okay, here's an example. Question. Practice exercise 724. A 19.5 liter sample of neon gas is cooled from 76 degrees Celsius to 38 degrees Celsius. What is the volume of neon in liters at this lower temperature, assuming the pressure is constant? All right, so word problems, right? We always have to like extract the information. So I see that we have a volume, 19.5 liters, and at the initial temperature is 76 degrees Celsius and is cooled down to 38 degrees Celsius, and we want to know the new volume. So we have this equation, and we're solving for V2, right? So we can rewrite it as V2. If we multiply both sides by T2, we get V1 over T1 times T2. But remember, we're not ready to just plug numbers in quite yet because the temperature values need to be in Kelvin. Right? So we can take each of these and subtract. I had that right the first time. 273K to get Kelvin. And 76 becomes 349K. And 38 becomes 311K. I just want to point out why this matters here for a moment, right? So we have, ultimately in this equation, we have T2 over T1, right? And if we use Celsius, we get 0.5, right? So it looks like, oh, temperature is half as much as it was before. But that's not really true, right? 311 over 349 is 0.89. So the temperature only dropped actually like 11%, not 50%. Okay, anyway, we can plug that in now. V2 is equal to 19.5 liters times T2, which is 311K, and T1 is 349K. So we actually already found out that this ratio right here is 0.89, so the volume should go down by that much, but we can go ahead and plug these in, and we do in fact find that V2 has gone down just a little bit to 17.4 liters. Does this make sense? Yeah, temperature goes down, volume should also go down. There's the work again a little bit cleaner for us, and we can see we got the same thing. Okay, let's move on to another relationship. This is Gay-Lussac's law, which relates this time temperature and pressure. Okay, so we already know volume and pressure and volume and temperature, so this one's kind of already built in, but we can still talk about it explicitly, right? And it is the case that if the number of moles and the volume are constant, then pressure and temperature are directly proportional. As one goes up, so does the other. So think back to this case here where we're heating one of the gases. In order to keep the volume from changing, you have to add more weight to push down, right? Which means you have to have higher pressure, and so pressure has to go up in order for N and V to be constant. So the relationship here is a nice directly proportional linear relationship again. Again, it's just remarkable that it's linear when you think about it. The fact that it's just such a nice clean relationship is wonderful. So same argument we made before, T is proportional to P, then the ratio is proportional to 1, and that applies to any set of P and T. And so if they're both equal to 1, then they're both equal to each other, and we get another equation like so. Okay, here's another question. Before leaving, your tire pressure is 35.2 psi. The temperature of the air in your tires is 25 degrees Celsius. After driving, the tire pressure is 36.5 psi. What's the new temperature of the air in the tires? All right, so we have P1 is 35.2 psi. T1 is 25.0 degrees Celsius. The new pressure is 36.5 pounds per square inch, psi. T2 is what we're solving for. Okay, a note about pressure units. PSI. PSI is perfectly fine pressure unit. It's non-standard. We don't have to change it into anything as long as they're the same as each other, right? Because ultimately, the equation that we'll have will be a ratio of pressures. So they'll cancel out, the units will cancel out. But as long as the pressure units are the same as each other, we can use it. Doesn't matter what they are. The only one we really need to worry about is Celsius. It has to be Kelvin. So that becomes 298 K. When we add 273 to 25. Okay, we're solving for T2, right? So this is actually going to take a couple steps because T2 is currently on the bottom of this ratio. So we want T2 to be on top. So we can multiply both sides by T2. And then we're going to multiply by the inverse of this ratio, or basically multiply by T1 and divide by P1. Then we get T2 is equal to T1 over P1 times P2. And sometimes I write it different ways, right? You might want to emphasize the fact that you have this ratio of pressures, right? We can see that if here we can really tell if the pressure goes up, then the temperature goes up by the same factor, or if the pressure goes down, the temperature goes down by the same factor, which we'll check for at the end after we put our numbers in. So we have 36.5 psi times 298 K over 35.2 psi, and that equals, just running out of a bit of room here, 309 Kelvin. I'll make it a little bit cleaner here for us. Okay, so same kind of setup, 309.16 Kelvin, or 36 degrees Celsius. It didn't specify which units we had to answer in, so either one is fine. And we double check that it makes sense. All right, so we've just encountered all these different simple laws. We've had 3 so far. A and B are kind of showing the same thing here. And what we're going to do next is combine these simple laws into one equation, which we call the combined gas law. We'll do that in just a moment.